Hi, everyone. As Rob said, I'm Tim Dresser, and I work on speed metrics in Google's Waterloo office. I'd like to take some time to talk about speed and Chromium. First off, when we're talking about speed in the context of Chromium, what are we actually referring to? We use it as a pretty broad umbrella term encompassing latency, smoothness, memory usage, power consumption, and binary size. And making sure we have a performant browser requires making intentional trade-offs among all of these dimensions. Speed has been one of Chromium's core principles since the beginning, along with simplicity, security, and stability. Speed is super important to our end users, as well as web developers, and positioning the web as a viable app platform. Speed is important to enabling the web to make information universally accessible, whether the user is on a 2G connection with a $50 Android phone or a shiny new laptop. Different contexts can result in vastly different performance, whether it's geography, platform, device, connection speed, or site. We've seen huge scrolling regressions which only apply to a specific model of a specific Android phone due to tiny differences in GPU. In order to reason about this massive variety of contexts, we need to be able to quantify performance to enable data-driven decision-making. Quantifying performance is key to identifying the highest impact performance projects, verifying that performance projects had the impact we intended them to, as well as the detection, prevention, and remediation of regressions. To quantify performance, we have a suite of performance metrics. Rob gave a lot of context on metrics in general in the previous talk. We're going to dig in a bit more into performance metrics in particular. I'd like to start off with a couple of quotes that I really like that relate to performance measurement, though. The first of these is by Peter Drucker, who stated, "If you can't measure it, you can't improve it. If we want to be able to improve the performance of Chromium, we need to be able to measure how fast it is." Another quote that I love in this space is frequently known as Goodhart's Law, although this quotation is directly from Marilyn Strathern. It states, "When a measure becomes a target, it ceases to be a good measure." So what this means is if we create metrics to measure performance and we focus solely on improving those metrics, we're likely to find ways that we can improve the metric without actually improving user experience. These two quotes are kind of in direct opposition. So how do we kind of reconcile the tension between these two ideas? I think we need to acknowledge that thinking without data is aimless, but data without thinking is dangerous. We need data to guide our intuitions when we're reasoning about performance, but we can never blindly make decisions solely because the data indicates that something is the right choice. One of the other ways we can mitigate the risk around Goodhart's Law is to measure user experience as directly as possible. This ensures that when we see a regression in our metric, we can be fairly confident it's a real regression in user experience, which results in us spending less time chasing regressions that aren't real. It also means that when we improve our metric, we can be confident that we're actually improving user experience. If I land a change and see that it improves my performance metrics, I can be confident that that change is doing the right thing. It's very tempting to focus on the details of the part of the system you're trying to optimize, but this can be risky. Suppose the 4 steps on this slide represent some process we care about. Maybe it's loading a page or responding to user input. If my team owns step 2, it's tempting for us to look only at the duration of step 2 when trying to detect regressions or quantify the impact of changes we make. If we only measure our part of the process, it looks like the state of the world on the right-hand side is a regression from the state of the world on the left, when in practice, we've actually just shuffled some work from step 3 into step 2. This happens constantly, and it can easily result in us wasting huge amounts of time hunting down regressions that aren't real. Instead of focusing on the duration of the second step, we should really be reasoning about the duration of the entire process, while still being aware of the cost of the second step. Low-level metrics help you understand what a system is doing and can help diagnose a regression or improvement in a top-level metric, but shouldn't be used to claim an improvement in speed and should be taken with a grain of salt when detecting regressions. When you're authoring a low-level metric, try to make sure it breaks down a higher-level metric. This means that when the higher-level metric moves, we can use that low-level metric to diagnose why it moved. And if we have a change that we anticipate impacting a low-level metric, we can easily state which high-level metric is likely to be impacted. Measuring user experience as closely as possible also ensures that we can share these metrics broadly, with confidence that the metric will be meaningful to site owners, web developers, Chrome engineers, Chrome leadership, and others. The Core Web Vitals are a set of metrics which Google recommends to external site owners and web developers, and we also use them as Chrome developers. The three Core Web Vitals are largest contentful paint, which reports the time from navigation start until the time the largest element was painted. First input delay, which reports the time from when the first input occurred until the page starts responding to that first input. And cumulative layout shift, which measures how much the content on the page jumps around. Cumulative layout shift arguably isn't really speed, but it tends to get put under the speed umbrella anyways. The data in this slide comes from Nick Jansma from Akamai, and he's looking at the correlation between cumulative layout shift, which I just mentioned, and the frequency of rage clicks. A rage click occurs when a user starts rapidly clicking out of frustration that the page is not behaving the way they expect it to. You can see here that as cumulative layout shift becomes more common, users rage click more. Users become more frustrated with the page. This is evidence that this metric probably does really correlate with something that our users care about. The Core Web Vitals are a tiny set of metrics with a broad audience, but there are many other performance metrics. Latency and smoothness is a broad category, including largest contentful paint and first input delay, but it also includes scrolling and media smoothness, startup latency, UI thread responsiveness, as well as tab switching time. The example you can see on the right is from our freeze-dried tab effort, which is an attempt to improve browser startup times by taking a snapshot of a web page and then displaying that snapshot before we've even spun up a renderer process. You can see that in the video at the bottom, as soon as the user taps on Chrome, we're able to show the page snapshot almost immediately, making the browser startup experience feel much lower latency. Memory is a bit of a slippery metric because the use of memory in and of itself isn't actually bad. Using memory that's required by other applications is bad, and memory on low-end devices is a major constraint to performance. But completely unused memory that nothing on the system wants to use is a bit of a wasted opportunity. We could be caching something more aggressively and reducing our latency. We definitely need to make sure that we're able to free up memory when needed, though. We also see increased memory consumption as devices ship with more and more RAM, which isn't actually a bad thing at all. This is an example of a metric that doesn't correlate directly with user experience, being difficult to reason about. Memory is used as a leading metric for latency. In many cases, as memory consumption goes up, our latency gets worse and worse. And it also correlates strongly with out-of-memory crashes. So memory is an important thing, but we need to keep some caveats in mind when we look at the metrics. We have some UMA histograms which capture memory split up across various processes. All processes is memory.total. And we also have renderer, browser, GPU, and extension memory per process. We measure the private memory footprint in all cases. A few years ago, there was a big push to reduce the memory consumption per tab. We verified the experiment in the lab, but in the wild, we didn't see any change in the overall memory consumption. We eventually realized that we were running into an example of something known as Jevons paradox. Jevons was an economist who noticed back in 1865 that the more efficient coal burning was, the more coal would be burned in total. This is kind of unintuitive. You'd think that the more efficient resource use was, the less of that resource we would use. But in practice, that wasn't the case then, and it wasn't the case with tab memory consumption either. We saw this exact same pattern. The more efficient tabs are in terms of memory use, the more tabs users open. This was an improvement in user experience. Users could use more tabs without Chrome slowing down. but it wasn't the improvement that we expected. I think the moral here is to be clear on what it is that you're trying to accomplish, and think about potential impacts on user behavior, as well as performance. One of the impacts performance improvements can have is enabling users to use the browser in new ways. Power consumption is another tricky metric, as it's user-facing sometimes when the user's on battery or their laptop becomes super hot. It's definitely something we need to keep in mind, but the numbers are difficult to interpret without a good deal of context. We track these numbers for Android using an UMA metric that looks at battery drain, and in the lab, we have some Android devices which are instrumented to give us high accuracy power consumption information, but we also end up utilizing proxies in a number of cases, such as CPU and GPU usage and the number of idle wake-ups. Binary size is important for a couple of distinct reasons. Desktop updates fail more often with a larger binary, and keeping the browser up to date is important for security, among other reasons. We're also shipped on the default Android system image, and the constraints around the system image require us to stay small. There are various tools available for understanding sizes, and size is measured on the commit queue as well as via a Garrett plugin. You can see the Garrett plugin output on this slide. I want to talk a little bit now about the life of a CL. This is similar to what Rob just talked about when thinking about metrics in general, but there are a few differences when we're dealing with performance. When you're writing a CL, whether you intend it to impact performance or not, you may end up needing to dig into its performance implications. When authoring a performance impacting CL, you'll often cycle between testing locally, testing in the lab, and experimenting in the wild. You'll start by authoring a CL and verifying that it behaves as expected with local tools. You'll potentially run the CL through our perf lab before landing, or you can just land it and look at the results in the perf lab. Finally, you'll have the CL landed and observe the change in the wild, ideally via an A/B test. If the change in the wild isn't what you expected, you'll go back to investigating the change in the lab or locally before making some changes and pushing the change again. Let's start by digging into some of the tools that are available for local investigation. The most important of these is probably Chrome tracing. Tracing allows you to annotate code with starting and stopping points, and then view these ranges across processes and threads. Tracing is great for understanding how a complex multi-process system is behaving. We're currently working on a replacement for the Chrome tracing UI, which will be based on this new Perfetto effort, which is migrating tracing from JSON traces to protobuf traces. I'm definitely excited about this. It's going to be improving a lot about Chrome tracing, but it's still not quite ready yet. Look forward to that. The memory heap profiler is integrated into Chrome tracing and gives detailed information about where memory is allocated across the various allocation approaches used throughout Chrome. Chrome histograms, as Rob mentioned, can also be used to inspect histogram values, which can be useful for a little bit of limited local performance debugging. And Chrome //UKM can be used in a similar way to locally investigate data output through UKM. In some cases, it makes sense to rely on OS-specific tools. ETW for Windows, SimplePerf for Android, Perf for Linux, and dtrace for OS X can all be extremely useful to diagnose certain kinds of issues. If you're going to try to do an investigation with one of these tools, I'd encourage you to reach out to others on the Chrome team who may have used these tools before and get a sense of the best practices. Once you've completed local investigation of a change, you'll want to see the impact via our performance lab. The performance lab runs around 1,000 tests across many different devices and platforms. It's used to detect regressions before releases occur. When a regression is detected, a bug is auto-filed and bisected via pinpoint. This being auto-filed is pretty new. This used to rely on a group of sheriffs, but now this is almost completely automated. When a bisection by pinpoint is successful, it automatically assigns the bug to the CL owner. If you want to get ahead of this process, You can also use a perf try job to run a CL through the performance lab before it's been landed. This is an example of the data gathered by the performance lab. On the x-axis, you can see the revision number. We don't test at every revision. We test kind of as frequently as we can, but we normally have a number of revisions lumped together. And when a regression is detected, as there was in the middle of the graph here, we automatically file a bug, trigger a bisect, and then assign the owner appropriately. Our performance lab will never be able to catch all regressions or estimate the magnitude of improvements accurately due to the massive diversity of devices and sites in the wild. When in doubt, trust data from the wild. Performance metrics from end users come in two different forms, as Rob discussed. This holds true for all metrics. UMA, which is metric which are aggregated into histograms, and UKM, which gives us per website metrics. When monitoring metrics for regressions, I'd encourage you to look at a couple of different percentiles. 50th and 99th is a good place to start, although you may also want to look at 75th. It's easy to miss changes in the broader distribution if you overfocus on a single percentile. And these metrics are often used to measure experiment impact via A/B testing, as Rob discussed. When something happens in the wild that we don't understand, we go back to the lab and local tools to figure out what's going on. Local tools tend to be much more actionable than the data we see in the wild, but the wild is much more able to really capture the magnitude of an improvement or a regression. Whether you're working on a performance improvement or building shiny new features, you will impact the performance of our product. Our users rely on us to access the information they need in a performant way, which respects their system's resources. Let's take this responsibility seriously and keep building a browser with speed as a core feature. Thanks, everyone. I think we've got some time for questions, and I'll be in the hallway track immediately after QA ends. Is there a good Slack channel for perf metric related questions? That is a good question. We don't answer questions nearly as promptly as we ought to, but the speed metrics channel in the Chromium Slack is the right place to ask questions. And we should do a better job of monitoring that. If you are asking questions there and we're not responding to them, I apologize, and feel free to send an email instead to speed-metrics-dev@chromium.org. Yeah, what are the biggest speed bottlenecks today? It's hard to answer that question generically, as I mentioned, there's just like a huge number of different things that contribute to speed. Some of the things that are on my mind as being really big problems, when we look at largest contentful paint and what causes largest contentful paint to be bad, one of the biggest problems, somewhat unintuitively from my perspective, is time to first byte. We see a lot of cases where devices are either just very far from the server they're connecting to, or servers take forever to start spitting out information. When I was digging into this using UKM data, I was able to look at some of the specific websites that are the worst culprits here. And there were sites where from my desktop connected to a good internet connection, it took 30 seconds to receive the first byte back from a server. This is a bit not super actionable for most Chromium engineers, but it is a large bottleneck. And then the other one that I feel like I have to mention is just JavaScript execution time. There are a lot of pages which are downloading massive blobs of JavaScript and just executing kind of 5 seconds worth of JavaScript on a moderately reasonable Android device. I think the V8 team has done a great job to do what they can to improve performance in these cases. And again, to some degree, it's not necessarily within the average Chromium engineer's purview to just optimize the engine and fix this problem. But working with framework authors to figure out what can we do to avoid these massive blobs of JavaScript, I think is important. All right, thanks everyone. I'll be in the hallway track if you have any other questions.